In this video, we're going to apply the fundamental theorem of calculus to evaluate some definite integrals. And this is the first part of the fundamental theorem of calculus. It says, if the integrand f is continuous on the interval from a to b, and f prime is equal to f on the interval from a to b, so that means that f is an antiderivative of little f, capital F is, then the value of this definite integral is just the antiderivative evaluated at b and then evaluated at a and then subtracted. So that makes this really very easy to find. We don't have to come up with Riemann sums and take limits as the number of rectangles goes to infinity. We can do this instead, and it's going to give us that same value. And that value, again, remember what that represents. If our function is positive, that's the area between the function and the x-axis on the interval from a to b. If the function is sometimes positive and sometimes negative, we get a net area. It's the area between the function and the x-axis, but any area that's above the x-axis will count it as positive, and then we'll subtract any area below the x-axis. So this integral can be positive, negative, or zero, but we can always interpret it as a net area. Okay, so let's actually practice doing this. There are no areas here. We're just going to practice doing this over and over again. Basically, the way you want to approach this is through a three-step process. I almost wrote a two-step process, but there is a very important first step that's often skipped in books. You need to find the antiderivative of f. That's the first step. Sometimes you have to rewrite f first so that your basic rules apply. So let's make sure we add that to our rules. So how do we use this? The first thing we do is we write f so that our basic antidifferentiation rules apply. And then after we do that, we just compute the antiderivative. And then we evaluate f at b and a and subtract. Super simple, very easy. Now, sometimes the trick is writing f so that the basic antidifferentiation rules apply. Now, this is the basic antidifferentiation rules sheet that I gave you. So we've got all of these rules that we've already talked about, all the way through the a to the x. We're going to talk about these later after we discuss integration by substitution. And then we've got these 6 rules up here, and we're going to discuss these after we talk about integration by substitution as well. So those are the only rules that are necessary. If one of these rules does not apply, you have to use algebraic manipulation or possibly trigonometric identities and algebraic manipulation to rewrite the integrand in such a way that your basic rules apply. So we do a rewrite, we compute the antiderivative, and then we plug in the limits and subtract. It's actually very simple, but remember, when you're done, you interpret that as a net area. Okay, so let's look at this first one. Oh, this is a great candidate for this. It's already written in a form so that basic rules apply. So all we have to do is take the antiderivative. So first you antidifferentiate. You don't need a plus c. So we bring our constant down, and then we're using this power rule. So we add 1 to the exponent and divide by the new exponent. Don't forget to add c. So we bring your constant down, add 1 to the exponent, divide by the new exponent, and then we bring the next constant down, add 1 to the exponent, divide by the new exponent, then bring the next constant down, add 1 to the exponent, and divide by the new exponent. The 4, the 3, and the 2, they all reduce. And then we're evaluating this expression from 1 to 2. So that means you just substitute in x equals 2. And you substitute in x equals 1 and you subtract. I like to see this step because when I see this step, that tells me that you understand the fundamental theorem of calculus. And then you can use a calculator for the arithmetic if you want to. The arithmetic is so easy this time, I'm not going to use a calculator for it. So I've got 16 minus 8 is 8. 8 plus 4 is 12. And then over here we've got negative, we're subtracting 1 minus 1 plus 1. So those ones reduce, so we end up subtracting 1. So we have 12 over here minus 1, that's 11. Isn't that nice? I think it's great. So much easier than adding up areas of rectangles, getting those formulas in terms of n and taking the limit as n goes to infinity. And we know that that doesn't even work all the time. That's just a very special case, and that it does work when the function's continuous. But there are other functions where we can't really do that. Okay, so over here we want to do the same thing, but this one requires an extra step first. Notice you've got a product. And there's no product rule for antiderivatives, guys. Nothing on here. You don't have an F times G rule. And please don't do this. A lot of students do. Don't take the antiderivative of that and multiply and add C. Please don't do that. It just doesn't work. That antiderivative times that antiderivative, if I take the derivative of that product, I do not get this back. So please don't do that. We need to rewrite this so that one of our basic rules will work. So we're just going to distribute. You've got a binomial times a binomial. After you distribute, it's going to look like this. You'll be able to use the power rule. Nice and simple. But make sure that you rewrite it so that rules apply. If it's a product like this, basic rules do not apply. So you've got to do a little rewrite. So we'll distribute so that our basic rules apply. First times first gives me an 8x cubed. Outer times outer is 2x. Inner times inner is negative 12x squared. Last times last is negative 3. And we're integrating with respect to x. Okay, now it looks like we're ready. We've got basic rules for all of these. So now we antidifferentiate. So I bring my 8 down, then I add 1 to the exponent and divide by the new exponent. Then I bring my constant 2 down. There's a 1 there. We add 1 to the exponent and divide by the new exponent. Bring our negative 12 down, add 1 to the exponent and divide by the new exponent. Antiderivative of a constant is the constant times your variable of integration, which in this case that's x. That's our antiderivative. We're going to substitute 0 and 2 and subtract. You may want to simplify the coefficients first. 4 goes into 8 twice, the 2's reduce. 3 goes into 12 4 times. So we end up with this. And then if we substitute in x equals 2, we get this. If we substitute in 0 for x, we get 0, 0, minus 4 times 0, minus 3 times 0. So that's all 0. So this gives us 16 plus 4 is 20. And then I've got 8 times 4 is 32. So 20 minus 32 is negative 12. And then we're subtracting 6. So that's negative 18. And that's our answer. So we antidifferentiate. And then this step right here, that's f of 2 minus f of 0. So you're doing f of b minus f of a. And then you want to simplify the result. And remember what that means. If I graph this function and I look at the area between that function and the x-axis on the interval from 0 to 2, there's more area below the x-axis and bounded by our function than is above the x-axis. And the net area is that negative 18. Okay. There's negative 18 square units of area below the x-axis, or there's negative 18 or 18 square units of area below the x-axis. more than the area above the x-axis. I'm having trouble with my English right now, but I hope you get the idea. Okay, here, I look at this, I say I've got basic rules for that. Do not be distracted by the theta. It's just a dummy variable. It's saying integrate with respect to theta. And I'm using the word integrate now because I've got bounds. This is called definite. This is a definite integral. This is integration. I always think integration gives me a number. Antidifferentiation gives me a function. But part of integration requires finding the antiderivative. So anyway, back to this. Don't be distracted by the theta. You're going to use the exact same rules that you would use over here. You just replace the x's with thetas. And it's ready for basic rules. So we can antidifferentiate. That's always the first step. Bring your 4 down. The antiderivative of sine is negative cosine. Oops, I said it, but I wrote the wrong thing. Antiderivative of sine is negative cosine. There we go. And you can always check the derivative of negative 4 times cosine of theta is a negative 4 times a negative sine of theta, which is going to give us a positive 4 sine of theta. That's good. Bring the negative down. And the derivative of sine of theta is cosine of theta. You don't need the plus c with these. Then you evaluate from 0 to pi. So we'll do f of pi minus f of 0. So we've got negative 4 times cosine of pi minus 3 times sine of pi minus negative 4 times cosine of 0 minus 3 times sine of 0. Be careful with the SIGN signs here. Cosine of pi is negative 1, sine of pi is 0. Sine of 0 is 0, cosine of 0 is 1. So we end up with a negative 4 times a negative 1, that's positive 4. So that's 4 minus 0. And then I've got a minus a negative 4 here, so we're adding 4. 8. The area under the curve is 8, or that net area is. Okay. So you antidifferentiate, substitute the bounds, and subtract. And then, of course, you want to simplify. And on your final exam, I want to see this step. I just want to see that you do this correctly. If you make an arithmetic error, I'm not too concerned about that. I'd like this to be accurate, but if you make a mistake, it's okay. I just need to see that you understand the concept of how the fundamental theorem works. Okay, so now let's look at this one. Well, notice that I don't have basic rules for these, not the way they're written, but I can rewrite them so that I can use my power rule. If you have an x in the denominator and that power is anything other than a 1, you need to bring that x up to the numerator so that you can use the power rule. Now, this is on the second page of your sheet. These are all the algebra rules that you need. Whenever I see 1 over x to some power, I can bring that up to the numerator. I can write that as x to the same power, but if that power in the denominator is positive, you bring it up to the numerator, it's going to be negative. So you just change the sign. And if there are constants involved, like this one, pull out the constant. If it's in the denominator and you bring it up, it becomes exactly the same thing, but with a negative exponent. Same thing here, you see that. So make sure you can still do this stuff, guys. It's very important in order to get accurate answers for your derivatives and antiderivatives. This is the second page on your basic antidifferentiation rules handout. Okay, so I see that and I say, I don't have a basic rule for that, but I can rewrite it using exponent properties. So we'll start by rewriting, and we'll use the fact that x to the negative n is 1 over x to the n. So I can bring that x squared up to the numerator if I make that an x to the negative 2. Now the constant here is just a negative 4. There's a negative 4 over an implied 1 there. So I'll pull my constant out. And then when I bring that x cubed up to the numerator, that makes that negative and -3. All right, now I'm ready to antidifferentiate because I've got basic rules for that. So we add 1 to the exponent and divide by the new exponent. Bring the -4 down. Then we add 1 to the exponent and divide by the new exponent. Substitute in 1 and 2 and subtract. And I would probably rewrite this first because I don't think in terms of negative exponents. So I'll think of this as a -1 times a 1 over x, because that x to the -1 can be an x to the first in the denominator. Then -4 divided by -2 is a +2. And that x to the -2 in the numerator can be brought down to the denominator that way. So we're here. So we antidifferentiated, and then we did a rewrite, or you could call that simplifying if you prefer. I just did that because it's easier for me to think this way. Now I substitute in my upper limit and my lower limit and subtract. So I've got my antiderivative evaluated at 2 minus my antiderivative evaluated at 1. Let's see, what do we get? We get -1/2 plus 1/2 happens to be 0 minus -1 plus 2. So I have 0 minus 1, so that's -1. And we simplify. It's not too bad. Okay, don't have a quotient rule for antiderivatives, so we're gonna have to start with a rewrite. Since this has 2 terms in the numerator, I'm going to separate that numerator. I'm going to say, if I've got something plus or minus something else in the numerator, and I just have a monomial, a single term in the denominator, I can do this divided by this plus this divided by this, and it'll work. It'll get me the right answer. It's equivalent to that because of the way we add fractions. So this is 4 over the square root of y. Because I'm preparing to antidifferentiate, I'll write that as y to the 1/2 power. Then I've got 6y over here. And we just used this property. The nth root of x to the m is x to the m over n. The index of the radical goes in the denominator. So, and then we also split up this fraction. So we use this property. If I've got fractions and they have the same denominator, we just add the numerators and keep the common denominator. Because those pieces of a pie, let's say, they're the same size. So if I've got like 1/5 of a pie and 2/5 of a pie, well, actually I've got 3/5 of a pie. Makes sense, right? Same thing works over here, it's just a little bit less concrete. If I have a fraction like this, and I've got a sum or difference of terms up here, well, I can do this backwards. I can do a over b plus c over b, and that's what we did. Okay, now we've got to rewrite these guys, and we're using that negative exponent property again. I've also got y to a power over y to a different power, so we've got to use this one. You subtract. It's the exponent in the numerator minus the exponent in the denominator. I hope this is not too bad. It's not difficult, it's just easy to forget how these things work when you're looking at these problems. But when I remind you, everybody's like, oh yeah, of course. Like, you remember this, you've done this before. It just looks a little different. So I bring my constant out, that's a 4, and it's a 4 over an implied 1. So you're bringing out that 4 over 1, which is a 4. And then you bring the y to the 1/2 up to the numerator. That's going to make that y to the -1/2. The constant here is 6 over 1, so that's just 6. You pull that out. And then you subtract the exponents here. That's y to the 1 minus 1/2, or y to the 1/2. Okay, so we did our rewrite, and now we're ready to antidifferentiate. So we bring our constant down, excuse me, then we add 1 to the exponent and divide by the new exponent. Negative 1/2 plus 1 is positive 1/2, and when we're dividing by 1/2, that's the same as multiplying by the reciprocal. Then over here, you bring the 6 down. Over here, you add 1 to the exponent. 1/2 plus 1 is 3/2. You're dividing by 3/2, it's the same as multiplying by 2/3. Then you substitute in 1 and 4 and subtract. 3 goes into 6 twice, so this can be simplified. This is 8 times the square root of y. And this is 4 times y to the 3/2. Now I'm going to write that a little differently. That's the square root of y cubed, because that 1/2 power is the square root. If I take that and cube that, I get y to the 3/2. I'm writing it this way rather than the square root of y cubed, or even just leaving it as a rational exponent, because I sort of think this way, and if I'm substituting in 4 and 1, it's easier to simplify if I see it this way. So I've rewritten it just for the sake of making the computation easier. And now we will evaluate at 4 and evaluate that expression at 1 and subtract. So that's f of 4 minus f of 1. And so we get 8 times 2, which is 16, plus, we've got 2 cubed, that's 8. 8 times 4 is 32. Over here, I'm subtracting 8 plus 4, so I'm subtracting 12. 32 minus 12 is 20. 20 plus 16 is 36. But it's, even though we did a lot, remember what we did. We rewrote it using all these properties. Then we antidifferentiate, plug in 4, plug in 1, and subtract, and then you simplify. Next one. Same idea, I got a product. We don't have a product rule for antiderivatives, but I can rewrite this. That's a t to the 1/3 power. So I'm rewriting using this property again. There's an n there and an n there. The index of the root goes in the denominator. And then we distribute. And remember that when you multiply those two powers of t together, since the bases are the same, you add the exponents. So this will be the integral from 1 to 4 of 2 times t to the 1/3, and t to the 1/3 times t to the 1st is t to the 1/3 plus 1, or t to the 4/3. So you do that. After your rewrite, you say, I do have a basic rule for that, so now we can antidifferentiate. Remember, the whole point of rewriting is to get the integrand in a form that you have a rule for. You always ask yourself, do I have a rule for that? If you do, just use it. If you don't, do a little algebra, do a little trigonometric not substitution, but use your trig identities to rewrite it. And remember these that we talked about before. If you've got a binomial or trinomial squared, sometimes you just want to square it. If you have a numerator, like we did on this problem, sometimes you want to separate that numerator and do this over this plus this over that. We have not talked about completing the square yet. Long division I'll save for Calc 2. We haven't talked about well-chosen 0. I'll save that for Calc 2. We have used trig identities a little, and then the rest of these we'll save for Calc 2. but we can expand expressions of a certain form, separate the numerator and evaluate two integrals, or use trig identities at this point. And all these other techniques will be added at the beginning of Calc 2. Okay, so we're here. We said we don't have a rule for that, but if we rewrite it, we do have a rule for that. So now we can anti-differentiate. So you bring the constant down, and then you add 1 to that exponent. Makes that 4/3. And then you divide by the new exponent. Dividing by 4/3 is the same as multiplying by 3/4. Then we add 1 to that exponent. 4/3 plus 1 is 4/3 plus 3/3. That's 4/3 plus 3/3 is 7/3. And then you're dividing by 7/3. That's the same as multiplying by 3/7. It's a fraction, so you flip it and multiply. We're evaluating all of this from 1 to 4. You can simplify the coefficients. 2 goes into 4 twice. And so we have this. We've got 3/2 times 4 raised to the 4/3 power. And I think I'm actually going to think of that as, I'm going to think of that this way. Something to the 4/3. Is that something to the first times that something to the 1/3? Because 1 plus 1/3 is 4/3. So this is actually 4 times the 3rd root of 4 plus 3/7 and or 3/7, and then we've got 4 to this power. If I've got something to that power, well, that's x squared times x to the 1/3, because 2 is 6/3, 6/3 plus 1/3 is 7/3. So when I substitute in 4 here, I'm going to get 4 squared times 4 to the 1/3, or a 3rd root of 4. Then we evaluate all of that at 1. So we get 3/2 plus 3/7. It's very ugly, I'm sorry. So 2 goes into 4 twice. There's nothing that simplifies over there. But we end up with 6 times the cube root of 4 plus this coefficient times the cube root of 4 minus that. I think I'll use a calculator because I don't want to waste too much of our time simplifying this. This is 16 times 3, that's 48/7, plus 6. So I've got 90/7 times the cube root of 4. Minus that. So I could multiply that one by 7/7 and multiply that one by 2/2. So I'll get 21 plus 6 is 27/14. Oh, that one's ugly. But again, what did we do? We anti-differentiated. Then we evaluate the expression at 4, evaluate it at 1, and subtract, and then we simplify as much as we can. Okay. Look at a few more. This one looks tricky, doesn't it? It's actually not too bad. I don't have a rule for this because, well, I don't have a quotient rule. And this does not necessarily simplify into something that looks like this. If you're thinking, oh, 1 plus cosine squared, isn't that something? It's not. 1 minus cosine squared of theta is sine squared theta. But 1 plus cosine squared theta doesn't really simplify to much of anything at all. But I do have this one term in the denominator, so I can split this up into 2 separate fractions. I can do 1 over cosine squared plus cosine squared over cosine squared, and I know at least cosine squared over cosine squared simplifies pretty nicely. That's a 1. So let's do that. We're separating the numerator. Anything divided by itself is 1. Love when that happens. Very satisfying when it just cancels. You get 1. And then 1 over cosine is secant. So that's actually secant squared. And that's very nice because we've got a rule for that, don't we? And if you're thinking to yourself, doesn't that simplify to something? No, 1 plus tangent squared is secant squared. 1 plus secant squared isn't anything. Okay, so what did we do? We separated the numerator. We're rewriting. And the way we rewrote it was we separated the numerator. And then we used trig identities. Use the fact that 1 over cosine of an angle is secant of an angle to rewrite that in this form. And then I look at it and I say, I have a rule for that now, so now I can antidifferentiate. So we rewrote until we had a rule. We rewrote here and we didn't have a rule for that, so we were still stuck. But you rewrite and you rewrite until you get to a place where you've got a rule and you say, secant squared, I've got that, is the derivative of tangent is secant squared. The antiderivative of secant squared is tangent, so we have a rule. Okay, so we did our rewrite. Now we're ready to antidifferentiate because we have rules for all of the terms in our integrand. Antiderivative of secant, or secant squared is tangent. Antiderivative of 1 is just a constant. The antiderivative of a constant with respect to theta is that constant times theta. It's always the constant times the variable of integration. In this case, our variable is theta, not x. So then you substitute in pi over 4 and 0 and subtract. So we've got tangent of pi over 4 plus pi over 4 minus tangent of 0 plus 0. Tangent of 0 is sine of 0 over cosine of 0. Sine of 0 is 0, so this is 0. Tangent of pi over 4, that's a 45-degree angle. 1 square root of 2 triangle. So that's going to be a 1. Opposite over adjacent is 1. So we get 1 plus pi over 4 as our answer. That's our simplified answer. So we antidifferentiated, we evaluated f at pi over 4, and we evaluated f at 0, and we subtracted, and then we simplify. This one looks really bad. It's actually not too terrible. Okay. Notice you've got a sign here and a sign here. I do not want to evaluate this as it stands. I could separate the numerator, but I don't see a lot getting simpler by dividing a sine of theta by secant squared theta. So I'm going to do something else. I'm going to factor out that sine of theta. Now everyone would approach, or people, lots of different people would tend to approach this problem in different ways. This is just the way that I wanted to approach it. Now, and that's because I have pretty decent intuition for these things. I've been doing this a long time. If you don't think of that, it's okay. It just might take you a little longer to get this into a form that you can integrate. So I factored out a sine of theta, and now I see this, and I remember an identity, 1 plus tangent squared is secant squared, so this can be replaced by secant squared theta, and then the secant squareds will reduce, and we'll just have a sine as our integrand. So we're doing a rewrite, and the way I chose to do it was I factored out the sine of theta, and then we're going to replace 1 plus tangent squared with secant squared, because those are the same thing. Whenever those are well defined, they're the same. So this is the same as secant squared. And that complicated thing turns out to just be sine of theta. So I'm replacing this with this. And the secant squareds reduce. Now I've got the antiderivative of sine. Antiderivative of sine is negative cosine. Evaluate at 0 and pi over 3 and subtract. So as soon as you're ready, you want to take the antiderivative. And you're asking yourself, when will I know that I'm ready? You'll know that you're ready when you have a rule for it. Antiderivative of sine is cosine, or negative cosine, so we know we're ready. Then we'll evaluate at pi over 3 and evaluate at 0 and subtract. So we'll have negative cosine of pi over 3 minus a negative cosine of 0. Cosine of 0 is 1. Cosine of pi over 3, it's a 60-degree angle. That's a 1, 2 square root of 3 triangle. The cosine of that angle is adjacent over hypotenuse, so it's 1 over 2. I have none of those memorized. I have 2 triangles memorized in a unit circle, and that's all I need to get me everything, any value that I need to find with special angles, you know what I mean. Okay, so I've got negative 1/2 minus a negative 1, so that's negative 1/2 plus 1, so it simplifies to 1/2. Now, this last one's not going to work out nicely because cosecant and cotangent actually, I'm not sure about that. Cosecant is 1 over sine of x, and cotangent is cosine of x over sine of x. On the interval from 0 to 4, that's going to be undefined at 0 and undefined at pi. We're going to have some problems. So I guess I need to pick an interval that doesn't include 0 or pi. This is one that I made up, obviously. It doesn't work out nicely. So an interval that doesn't include 0 or pi. Let's go from 1 to 2. There we go. We avoid 0 and pi. All right. So I just wanted to put this out here so that we could practice these rules. These are all ready. We're ready to antidifferentiate. We've got rules for all 3 of these. If you have a constant, bring that constant down. The antiderivative of e to the x, it's the easiest, it's just e to the x. And then we bring the negative down. The antiderivative of a to the x is a to the x divided by natural log of a, natural log of the base. Bring the 4 down. The antiderivative of cosecant of x, cotangent of x. Remember what that is? What do you take the derivative of to get cosecant times cotangent? If you said negative cosecant, you're absolutely right. So we'll have a negative 1 times cosecant of x. That's our antiderivative. We're evaluating from 1 to 2. Now it's not going to simplify very nicely, but at least the function is going to be well defined. Remember, the fundamental theorem of calculus only works when this function is continuous over the interval. And the original interval that I stated here had problems. We had vertical asymptotes on that function. Okay, so now we're going to plug in 2 and 1 and subtract. So I've got 5e squared minus 3 squared, that's 9 over natural log of 3, minus 4 times cosecant of 2, minus 5 times e minus 3 over natural log of 3, minus 4 times cosecant of 1. That's our answer. Maybe we should try to simplify it. Got 5e squared minus 9 over natural log of 3 minus 4 cosecant of 2 minus 5e plus 3 over natural log of 3 minus a minus is going to be plus 4 cosine or cosecant of 1. The only thing that we can really simplify is this and this. It's like I've got negative 9 of them over here, plus 3 of them, so I've got negative 6 of them total. I guess we could group the e's together. We've got 5 times e squared minus e, minus 6 over natural log of 3. And I could group the cosecants, plus 4 cosecant of 1 minus cosecant of 2. If you're saying to yourself, that doesn't even look like a number, you're right, it doesn't look like a number, but e is about 2.7. Natural log of 3 is a decimal. We can find out exactly what that decimal is by putting that into our calculator. Cosecant of 1 and cosecant of 2 are well defined. Just find 1 over sine of 1 and 1 over sine of 2. Those are going to be just fine. So those are all numbers. We could get a numerical approximation if we used our calculator, but this is the exact answer. We're done. Okay, so that is how we apply the fundamental theorem of calculus. We just tend to do a lot of rewriting, and then after we rewrite, we anti-differentiate, plug in the upper limit and the lower limit, and subtract over and over again. This video wasn't about that, but remember what this represents. These numbers at the end, when you're done, they represent area under a curve. It's the area between the function and the x-axis, between x equals a and x equals b, but it's kind of a net area. It's the area bounded by that function in the x-axis, and we count the area above the x-axis as positive, and any area below the x-axis, we subtract that area. So this 11 here represents a net area. It's area above the x-axis on the interval from 1 to 2, and below this function, minus any area below the x-axis and bounded by this function on the interval from 1 to 2.